Welcome to module F, lecture 3. In the previous lecture, we told you how the road network normally gets developed, starting from a village area with one or two really good roads, all weather blacktop or concrete road, and then slowly targeting at least to get all weather road connectivity to ensure connectivity of all the nodes. That is the first, or the level 2, that is the first target rather. And then I said that with more and more population living in urban area, more travel demand, people start developing more and more roads to give direct connectivity with shorter travel time or shorter travel distance, sometimes to decongest some of the existing roads, build another road. So, finally, in fully developed network, you have multiple path. And in the context of the first target, that when we are trying to get at least what is the minimum road length that we should have, so that we ensure connectivity of all the nodes. In that context, I told about the minimum spanning tree, discussed about the two properties, possible multiplicity, also the uniqueness when every link the cost is distinctly different. And then we also discussed about two algorithms, Kruskal's algorithm and Prim's algorithm, which may be used to obtain the minimum spanning tree. With examples, we discussed and explained to you how stepwise or step by step how we find out finally the minimum spanning tree. But then that was like stage 2 development, where we just have basic minimum road to ensure connectivity of all the nodes. From that point onwards, with more and more population, with more urbanization, we start building more and more additional links, and every time we are building a new road or new connectivity we are doing, we are creating loop, alternative path, right, for one or more OD pairs. So, like that we keep developing the road network, and finally, in a fully developed urban area, the problem is very different. There we have generally multiple paths or alternative paths available if we want to travel from one origin to another destination, and such kind of alternative paths are generally available for majority of the OD pairs, right. So, in that case, as you know, normally everybody tries to travel by the shortest path. So, if I can travel in 20 minutes using a path, naturally I will not select a path where it will take 40 minutes or 30 minutes. So, for everybody it is so, all of us we would like to travel using the shortest path or in the fastest possible time. So, in that background, now we need to understand that what is the shortest path and how we can calculate the shortest path. So, in the context of shortest path, what we are trying to find out a path between two vertices or two nodes, such that sum of the weights of its constituent edges is minimum. Sequence of links, I can follow some sequence of link or another sequence of link to reach to the same destination. Like that, there are many alternative paths. I am only selecting that path where sum of the weights of its constituent edges is minimum among the alternative paths. Formally, given a weighted graph and one element V of capital V, that means one node of all the vertices or all the links, all the nodes that are there in the network, find a path from one destination to another destination, so that within this pair the total travel time or the travel cost is minimized. Again, cost and time are used interchangeably. Time is also a cost may be the direct cost of travel, length, maybe direct vehicle operating cost. It generally represents what you are using as deterrence. If you use cost, you are minimizing cost. If you are using time, then you are minimizing time. Whatever is the deterrence that you are using, that we are optimizing, we are minimizing by selection of the path, which is the shortest one. Like we said, two algorithms for minimum spanning tree. Here also we are going to discuss two algorithms for find out the shortest path. Both are very popular algorithms. The first one is Dijkstra's algorithm. I shall little bit of course describe it in this form, but it will be easy for you to understand, and for me also it is easy to explain with an example. So, we shall definitely spend more time there to explain you, but let us try to give you some overall idea first before we take an example and then explain you the steps. In Dijkstra's algorithm, we try to find out shortest path from one origin to all other destination node, when every link has non-negative cost. So, one very fundamental assumption, and of course, it is a very realistic assumption, the cost is non-negative. How the time length or cost can be negative in this sense? In this traffic assignment context, network context, in this context it can never be negative. So, what we get by the time we complete one set of iterations of this algorithm, apply it, we get from one home node, that is my starting node, to all other nodes in the network, what is the shortest path, that we get. Now, remember that many times I have seen students have confusion or they get confused between Dijkstra's algorithms. They do a lot of confusion between Dijkstra's algorithms and Prim's algorithm. Prim's algorithm is giving me the minimum spanning tree. That means, what is the network or a network that will ensure connectivity to all nodes, n nodes, with exactly n minus 1 link and with total minimum length or total minimum cost. Whereas, Dijkstra's algorithms, we are trying to get shortest path tree, or you can call it SPT or shortest path, from one given node to all other nodes in the network. So, what from, if I am starting node is 1, then 1 to 2, 1 to 3, 1 to 4, 1 to 5, for every destination what is the shortest path and what is the sequence of links that we need to select to reach to that particular destination as per the shortest path, that we will get. Steps. First, we assume that two types of level we will do here. Let's understand it in this manner. One is a temporary level, another is a permanent level. So, at any stage when I am applying this algorithm, every node will have a level, either temporary or permanent, right. So, as we move stepwise, iteration wise, then you will see that in every iteration one node we shall level permanently. So, once the permanent level is done for a node, we are not going to change anything there, because that is why it is permanent. So, once it is leveled permanent, that means we are not going to change it anymore. Other nodes, tentative level will be there, then tentative levels will keep changing from one iteration to another iteration. That means, still we have not finalized. So, they will keep changing, but every iteration one node out of those temporary levels we shall make it a permanent level. So, if I have got, generally speaking, n number of destinations I have to find the shortest path, then I will require n iteration. Every iteration one node will be leveled permanently. So, initially what we are assuming, that from my starting node to all other node, the cost is infinity or very large value, infinity or very large value. So, my cost is a very large value, and except for the starting node, because I am starting with a node. So, that is my origin node. So, there the cost will be 0, and I know the predecessor of that node is also that particular origin node. For all other nodes, we will assume the cost as infinity, and you can even assume the predecessor as the starting node. Sometimes we say that explicitly, sometimes we may not say that explicitly, but the cost is taken as infinity or very high value. Now, starting with that node, we explore now more and more possibilities in every iteration, and wherever we will find that by changing the predecessor what is assigned till the previous or in the previous iteration, that is the update. If I am doing nth, any jth iteration or any kth iteration, then k minus 1th iteration, whatever was the temporary levels, those are the best solutions so far. See, if I find by changing the predecessor what I am discovering now in this iteration, if I by changing the predecessor, if I can reduce that cost further, then I will change the predecessor and update the cost. Otherwise, my temporary level will remain as it was there in the previous iteration. And end of this iteration, with all the finally updated temporary levels, wherever the cost will be minimum, I will that node I will transfer from temporary level to permanent level. That is what it is. So, let us take an example to go each or to go step by step. I have taken an example where we have 6 nodes 1, 2, 3, 4, 5, 6, and the links are given as per the existing connectivity, say 1 to 2, 1 to 3, 2 to 4, 2 to 5, 3 to 5, 3 to 4, 4 to 2 is there already, 3 is already there, 4 to 5, 4 to 6, and 5 is connected to 6. Those are the connections which are existing. Other connections are not there, and in each case what is the cost that is known. So, let us say now we want to find out shortest path from node 1 and as I said, what Dijkstra's will give from one home node to all other home node. So, we eventually want to find out using Dijkstra's algorithms in one set of iterations the shortest path from 1 to all other nodes. That means 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6 stepwise. So, what I said first step is, you can say first step, you can say 0th step, it is all the way you want to define it. The very first thing assumption is that except for 1, if 1 is my starting node, then for 1 the predecessor is definitely 1, because that is my starting node, and the cost is 0, because that is my starting node. For all others in the beginning, I have not even looked at the network, but I will assume the cost is infinity, and you can also assume that the predecessor is that node or 1 or whatever it is, right. Predecessor is that node itself, you can consider, or predecessor is 1. Okay. So, let us say predecessor is 1, the home node, and the cost is infinity. Here the predecessor is really not so important, but main consideration is the cost. Eventually, we will assign the predecessor also, because that is the way the links will get explored, or connection will get explored. So, that is what I am showing here, my step 0 or step 1, whatever you say. For one node, you see that in blue it is written as 0, because that is the total cost, it is the starting point, and to 2, 3, 4, 5, 6, the cost is infinity, because I still do not know which path I am going to take, what are the costs, nothing is known. Okay, I have not even looked at the network. I have only identified my starting node, and I know starting node the predecessor is that, cost is 0. For all others, it is infinity. Fine. So, nothing, you can follow the table 1 to 1 0. So, in a way I can only permanently level my starting node, which is node number 1 here, with predecessor 1 starting node, because that is the starting node, and cost is 0. That is where I am starting. Okay. Now, 1 is established with 0 cost and 1 as the predecessor node. Now, my next iteration. Now, 1 is established. So, now I am looking at the matrix or looking at the connectivity. Here for the classroom example, or when you are explaining, we will look at the graph, but actually the algorithm will work, it will take a matrix, okay, and as per that it will start doing the calculation and explore various possibilities. So, 1 is connected to 2, because that is the connection which is existing, and I know from 1 I have reached to 1. So, I know 1 to 2 exist, 1 to 3 exist. Let us say 1 to 2. Now, I know that 1 to 2 the cost is how much? 10, and what I assumed as the cost? Infinity in the beginning. Predecessor, as I said, it is not so important, you can, but whatever it is, you can consider the predecessor as 1 starting node. But now, I have find out an alternative path. Maybe even if you take the predecessor as 1, it is still now 1, but I have found out another path rather than my assumed cost. I have actually discovered a path where the cost is 10. So, if I travel to 2 from 1, I have a connection, and where the cost is 10, and 10 is lesser than infinity. So, what I need to do? I will update my cost as 10 instead of infinity. So, that is what is written in green, infinity is taken out, because 10 is lesser than infinity. So, I have got 10 and I have made my predecessor now as 1 for this node 2. So, this blue arrow in the table below the graph, here the connections are shown. You can see. So, 1 is connected to 2 and similarly 1 is connected to also 3 and the cost is 9. Now, 9 is again less than infinity. So, I will connect, I will update the cost and with predecessor as 1. So, I know that I can come from 1 to 3 with a cost 9, which is lesser than the infinity. The remaining 4, 5 and 6, I have no information till now. I do not know. So, my cost still remains infinity and that is what is my present condition of tentative list, tentative levels. Done. I only explored 2 connections, 1 to 2, 1 to 3. Both cases I found that with 1 as predecessor, if I connect it directly 1 to 2, then my cost is lesser. So, I have updated. Now, I am not writing the for vertices 2, the cost is infinity, but I am writing the cost as 10. For 3, node 3, I am writing now the cost as 9, not infinity, and I have written the predecessor correctly. For all others, I have not indicated the predecessor. If you want, you could still keep it, but the cost is infinity. Now, I said that every iteration I will permanently level one node. So, now I look at this distance or the cost, whatever cost, distance, whatever you say. Now, I look at this list, I find my values are 9, 10 and remaining are infinity. So, among all these values, what is the least one? 9. That is for what? For what is or node 3. So, 3 I am permanently leveling, I am transferring 3 from tentative levels to permanent level. So, you can see this final SPT set. Now, 3 is transferred here. Earlier, I had only one node, node number 1 with predecessor 1 cost 0. Now, I have permanently leveled also in this iteration node number 3 with predecessor 1 and cost as 9. So, node 3 will get transferred from temporary level to permanent level. It will not, 3 will not go back again to that temporary level, because we are not going to touch it anymore. Now, one pertinent question could be in your mind that how we can be so confident that 3 we can no way reach through any other possibilities with a lesser cost. What could be the reason? The reason is very simple. We said one assumption, the cost is non-negative, right? Either it is 0 or some positive value. In all practical case, it will always be a positive value. So, look at this thing. I know 1 is connected to 2, 1 is connected to 3. Maybe 2 is further connected to some other node, which may eventually get connected to some other node, and I may always explore some path to come back to my node 3. But then can the cost be lesser than 9? No, it cannot, it is not possible. Why? Because I want to through 2, if I want to explore anything, the cost will always be 10 plus something, and I already know that 9 is even lesser than 10. So, any path through 2 will always have cost 10 plus, 10 or 10 plus. So, I am saying there cannot be any better path. cheaper path. So, just permanently level 3. Once I have done 3, now my new connections are there. Now, I discover okay, I still have 0 to 1 to 2 in the temporary level with 10 cost, but now 3 is also discovered with cost 9. Now, 3 is connected to 4, connected to 5. Now, if I want to go to 4 using this path 1, 3, 4, then my total cost is 9 plus 6, 15. 15 is less than infinity. 15 is less than infinity. So, I will update the cost of 5 from infinity to 15. That is what I have done, and also change the predecessor of node 4 as 3. That is what I have done. So, that means I am saying 4 predecessor of 4 is 3, predecessor of 3 is 1. So, you can always trace back. You know the path what it is going to follow. So, I have updated the cost for node 4. Similarly, 5, if I want to go 1 to 3 to 5, then 9 plus 6, 9 plus 12, 21. 21 is lesser than infinity. So, I will change the temporary level. So, for 5 the predecessor becomes 3, cost 21. For 6 I have no information till now. So, my temporary level, as per my temporary level, my costs are 10, 15, 21 and infinity. Which is the cheapest? 10. For which vertex or vertices or which node? 2. So, 2 is now permanently leveled. So, I have shifted 2 to the final SPT set with predecessor 1 cost as 10. So, remaining I have 4 with 15 cost, 5 with 21 cost, 6 with infinity cost. Now, let us go to the next step. Now, 4 is also permanently leveled. So, I have explored more. I know that 4 is also connected to 6. Okay. 4 is so 4 if I consider, so what we did, sorry, 2 and 3, 4 we have not yet taken. Okay. So, the next connections, so far I have permanently leveled 1, 2 and 3. So, 2 is permanently leveled. So, from 2 I have now again explored 2 to 5 and 2 to 4. Now, if I go to 5 from 2, my cost is 10 plus 12, 22, and 5 it is 10 plus 12, 22, and if I go what was my earlier cost? My earlier cost was 21 from 3. So, 21 is lesser than 22. So, I do not update. I do not update. So, although I am exploring new connections, I do not update. So, I have written the SCCA with 2 as the new node, permanent level node. I have explored this connection 4 to with predecessor as 2, but cost is 25, and for vertices 5 or node 5 with predecessor, so it is 22, but in both cases for node 5 if you take earlier it was 21, now it is 22. So, I do not update. For 4 earlier it was 15, now it is 25. again 25 is higher than 15. So, I do not update. So, I do not change the predecessor, I do not update the cost, my temporary level for 4, 5 remains same. So, now my levels are 4, 5, 6, 4 is having the minimum cost 15. So, I now permanently level 4 and transfer 4 there. So, 1, 3, 2, 4 permanently leveled. Next, once you have level 4, my new connection here is 4 to 6 and 4 to 5. So, 6 again get updated because 6 was infinity so far. So, now I find if I take 1, 3, 4, 6, then 9 plus 6, 15 plus 4, 19. 19 is lesser than infinity. So, I take it, and with 4 if I go to 5, then my cost will become 9 plus 6, 15 plus 7, 22. But 22 is less than higher than 21, already the other path which is there till now. That means 1 to 3 to 5. So, I do not update that. So, I have deleted that temporary thing. We considered, but we did not update, just delete it. So, my update is now 5 and 6, these are my 2 nodes. 5 case the predecessor is 3, cost is 21, 6 predecessor is 4, cost is 9. So, I now permanently level 6, and then next only the 5 will be remaining. So, 5 also comes. Okay. So, that is the way. Now, you have shortest path from one home node, that is in this case 1, to all other home node 2, 3, 4, 5, 6. Each case you know the predecessor, then that node, say for I know 1, 3, 4, 6, 6 predecessor of 6 is 4, predecessor of 4 is 3, predecessor of 3 is 1. So, I know the path 1, 3, 4, 6, and what is the cost that you get from this table. So, that is what is my shortest path, how it is going, and right side table tells me what is actually the cost. So, in this course, in this particular lecture, we discussed about, told you about the context of shortest path, why it is important, and one algorithm, Dijkstra's algorithm that we said, and we have shown you with an example how Dijkstra's algorithm can be applied to get a solution. So, with this I close this course, this lecture, and we shall continue in the next lecture. One more algorithm I would discuss, that is called Floyd's algorithm. Thank you so much.